we've been informed on a wider scale. 5, logistical arrangements. 6, baseline survey and mapping of water infrastructure as a basis for monitoring and evaluation. And this was through we started with the pilot in Baringo County. Under determination of water infrastructure variables, the variables were actually identified in a participatory manner, where all our professionals were included in identifying their various data needs, and we developed the tools. The other variables that were included in the tools included infrastructure completion status, operational details such as quantities, quality, energy use, chemical use, etc. Water quality as can be seen with our eyes, infrastructure availability around the year in terms of seasonality, implementing urgency, e.g., in addition to others like costs, source of funding, and ownership of the infrastructure, types of infrastructure management, functional status, and related details. And then we also took photos to show in situ characteristics at that particular time. Development of the data collection tools. I think we worked with Mr. Wamiti and the KW team to develop the 3 sets of tools or questionnaires that were used to collect data on the infrastructure. The first type of questionnaire that we developed was household mapping questionnaire, which was used to collect data on the households that relied on the infrastructure for the purposes of accessing water and sanitation services. The second one was infrastructure mapping questionnaire, which was used to collect data on water and sanitation infrastructure, excluding large dams. We had a third questionnaire which was to do with dams, large dams, and this one was specifically for large dams because there are various specific components of the project that we needed to map. Under development of online data forms, the team used Open Data Kit platform to develop the data collection tools using Copo Toolbox. This is a suite of tools for field data collection for use in challenging environments, that is remotely. The software is free and open source. Then the suite consists of a server for archiving large data sets and an application for data development. Users can create various forms of data sets without developing new data sets. Now let me zoom on to the pilot that we did in Baringo. So the agency elected to pilot the tools in Baringo County, mainly because in Baringo County we had done a program of boreholes, which was 100 boreholes, and that was financed under funding from JICA. So they provided an easy starting point for us to, in terms of locating where they are and taking the details we wanted. Then in Baringo also we have 2 large dams which could be used to map, to pilot the instrument for large dams. So features of ODK, we have the form builder application. We have designing forms quickly and easily, reusing existing questionnaires, building complex forms, having many different questionnaires, and easily sharing project data with colleagues, and then importing and exporting XLS forms, and importing via URL. Now, maybe go up a little, where the illustrations are starting. So in that illustration, we are showing the types on the screen, the types of infrastructure mapping forms that we developed for the purpose of collecting data online. And they are the three types of infrastructure forms, which include infrastructure mapping, investment, large dams, and then household forms. In the next one, we are showing the infrastructure mapping form alone. So we are showing that the forms deployed, the three forms deployed can be accessed by clicking on various tabs, and the tabs include the summary, where we can view the summary of information collected on a daily basis, form for editing, previewing, replacing, downloading, and sharing, sharing the data and cloning the forms. Then there's the data click, which you can use for viewing reports, tables, photos, etc. Then there is the setting for various forms and maps for viewing data on the map. So the next one is the results, the map that was generated after we keyed in the information. And this one is for the infrastructure that we had mapped. When you click on the item or the point, you'll see attributes of every asset that was mapped in that system. There we have large dams, and equally, if you click to a point, it shows you the attributes of that dam. And our forms were very elaborate, so we decided to pick a few indicators that you can click on the dot and you see. So when you click on the dot, that is what you see. You see the information that we have accepted that it can be seen. And you can copy and export, and then you analyze from wherever data analysis tool that you have. We have household mapping. Also, for every asset that we mapped a few of households that were relying on that asset to give us an indicator of distance of where they reside and what distance do they move coming to fetch water or accessing the services that we are offering through the asset. There are some of the dashboard features of the system. You can get various charts from the system. So I'll not, because of time, I'll not talk about this. And here we are looking at how we can download the data into our server and use it from there. These are things, the same thing there. I think the next thing I need to talk about is lessons that we learned about from this pilot, so that we can do a wider mapping exercise for all the assets within our area. So number one is that distances between project infrastructure in the field can be very long, so enumerators need to be facilitated well in order to move closer, to move and collect the information that is required efficiently. Number two, subsequent successful implementation of the system requires partnership and technical alliances, i.e., grassroots players to collect and update data periodically, timely and efficiently. Then We have Water Works Development Agency using the information to calculate and make decisions that affect the improvement of services on the grassroots. Then for household mapping, beneficiaries need earlier communication so that they can be free to share information. We realize that some customers would feel like maybe you are investigating them for other purposes, but we wanted only to get information about their use of the assets that we were mapping. All logistics should be planned and executed correctly for smooth fieldwork. Most importantly, enumerators need to be comfortable in the field to collect data without problems. The other lessons we learned is that local guides, those local assistant chiefs and village elders are very important in terms of providing guidance to enumerators in the field to access where the assets are. Then, most importantly, while water and sanitation infrastructure mapping is very important, it costs a lot of money in terms of being able to fund consultancy services, cost of enumeration, ICT and GIS hardware, software, and logistics. This calls for direct government funding and the support of development partners, because we in our budget only projects are funded and maybe recurrent expenses. Investing in this GIS are maybe not really mainstreamed by the government, so we need to have a paradigm shift in the budgeting process so that we advance the issue of monitoring and evaluation using the new technologies that we have in the sector. Then the system can be used to measure project outcomes, and for measuring impact, probably we need to supplement it with tracker surveys. Then new project designs, we are suggesting that every project that we are designing should have your spatial data, so that we are able to collect it easily and continue monitoring as it's being developed. Then, in conclusion, public institutions need to mainstream whole project cycle monitoring and evaluation, which feeds into the public sector knowledge management to ensure decisions made today contribute to tomorrow's livelihood in a sustainable manner. This calls for public investment in systems that enable sharing of real-time data in the practice of public investment and service delivery. There is need to harmonize water sector operations while sustaining the autonomy of sector institutions as provided for in the Water Act 2016. In this sense, a water mapping system like the one we are talking about is necessary to achieve that harmonization. This type of system will shed light on the current distribution of water and sanitation infrastructure and information on optimal future investment, gaps for universal access to water and sanitation services. And I think in our case, we are focusing on M&E, but it can be used by all other professionals in the agency in terms of investment planning and day-to-day operations. So that is the end of my presentation. Questions?
Thank you so much, Hikaji. We would invite a question, one or two. I'll only restrict it to two to Mr. Hikaji. Please. It was a platform for data collections and water mapping and water resources management. Okay. It seems they are very comfortable with your delivery.
I was audible.
Sure. Thank you so much. I will now be a little bit candid with the subsequent presentation. In terms of time, So I'll invite the next presenter is Margaret Kasuki, coming in with the determination of causes of reservoir sedimentation using GIS and remote sensing, a case study of Kalundu Dam in Kitui County. Margaret, the floor is yours. Please be mindful of the time.
Okay, thank you, and good afternoon. My name is Margaret Kasuki, and I'm from Kenya Water Institute. I'm presenting a study on reservoir sedimentation using GIS and remote sensing, a case study of Kalundu Dam in Kitui County, Kenya. Next slide, please. In Kenya, many dams that are located in arid and semi-arid areas are experiencing serious sedimentation, and this is causing water severe challenges such as water management, flood control, and production of energy. Next slide, please. And I chose Kalundu Dam because it is representing one of the dams that are located in arid and semi-arid areas. This dam was constructed in 1950s, and it had a capacity of 300,000 meter cubic. It is silted up in 1970s and was rehabilitated in 2013 with a capacity of 500,000 meter cubic. And the dam is silting up very fast. Like you can see, that is the spillway, and all this is silt. And you can imagine if it was just rehabilitated in 2013. Now this is the scenario as we talk of 2019. That's how it's looking like. Then for data collection, I processed DEM. And for land use, land cover data, I obtained it from Landsat 8 for the period of 1999 to 2019. And then this is the dam. The black part is the dam, and the black line shows the river that is feeding the Kalundu Dam. And now I came up with a map that is showing different types of soils in Kalundu Dam. We have the red soils. That is Kalundu River subbasin. We have the red soils, we have the sandy soils from the yellow, you can see the yellow, and then we have the brown soils, the brown parts that are showing the brown soils. I also came up with the drainage pattern of this subcatchment, and it has a dendritic drainage kind of a pattern. And then this subcatchment is very, very small. It's just 24 kilometers square. And this is an example of a Landsat image for 1999, but have not classified because the study is still going on. And then I also did the land degradation index map for the catchment, but the catchment is very small. Very small, so it was it didn't show much significant change in forest, but I decided to look at the neighboring catchment that is within the whole of Kitui County now, and you can see the you can see the red patches are showing high decrease in vegetation cover, and the green is showing high increase in vegetation cover. But when you can see that Kitui County, the way the blue lines are, it's all about the Kitui County. You can see that the vegetation is outside the Kitui County, and the Kitui County is experiencing too much of decrease in vegetation cover. And then I said it's an ongoing study, so to determine the soil loss from different parts of the catchment, I will use the muscle factor and I'll apply GIS software. Thank you very much. It is an ongoing study that is yet to be completed. Thank you.
Thank you so much. Thank you for keeping your time short and on point. Would you take question? Any question for Margaret? On the Kitui Dam, sedimentation must be a very big problem that we have in terms of the efficiency and the capacity of so many dams. It's a problem not only in Kitui, in so many areas I know because of the land use change. Any question? Okay, thank you so much, Margaret, for your time. We'll go to the next presenter that's online. Felix Kasiti, with the application of variable infiltration capacity module to support water resources management in Rufiji Basin in Tanzania. Felix, if you can hear us. We can't hear you, Felix. We can hear you, but the volume is low.
Felix?
Yes, sorry, I'm trying to increase my volume. Hello?
Felix, I can't hear you. You're a little bit far away.
Can I be heard clearly now?
Felix? Felix? Felix?
Hello? Can you hear me?
Yes, we can.
Yes, because we are hearing you.
So can I go on?
Okay, Felix, you can proceed.
Okay, thank you so much. Thank you for the organizers for giving me this chance to present our work that we are doing in Tanzania. The title of my presentation is the application of the variable infiltration capacity model to support water resources management in Rufiji Basin, which is in Tanzania. This is implemented under the Severe program, which I will not mention so much because it was covered by Dr. Mugo. So just a brief introduction on what the variable infiltration capacity is. It was developed by the University of Washington, and it's a semi-distributed macro-scale model that solves the full water and energy balance. So how big variable infiltration capacity of big works is that it simulates the fluxes within one grid cell, And to route that or to get stream flow or any other output at a point that you need, you have to incorporate a routing model, for example. So for stream flow, you have to incorporate a routing model, but other outputs are presented or are given as an outputs at a grid scale. So the model works. Hello?
Yes, we are getting you.
Okay. So the model works in a way that the cells do not communicate between each other, and only water only enters the cell from the atmosphere. So there are three inputs that are defined in a global parameter file, which is the soil parameters, vegetation parameters, vegetation library, and the meteorological forcing files. So the global parameter file is what is used to run the model. Some of the inputs that we use to run the model is a DEM, which is 30 meters. The resolution can vary depending on the area or extent that you are working with. And we use Google Earth Engine for all our pre-processing, except when you're trying to delineate a watershed. That's when we use GIS tools like ArcGIS or QGIS. The land cover data, we use MODIS at a 500 meter resolution. Because for our case, we are running it at a 0.05 degrees cell resolution, which is 5 kilometers. CHAP's daily precipitation data is used as an input. We also use drainage direction from hydroshed. Soil data, harmonized world soil data is used as input data. ERA interim data that gives temperature, maximum temperature, minimum temperature, wind speed from the ECMWF platform, and other input files, input data such as leaf area index, LAI, and albedo, which are in raster form. The study area, as I mentioned, is Great Ruaha, which is one of the major basins in Tanzania. So for this presentation, we have only focused on a sub-basin within the Great Ruaha basin. So the workflow is that to model VIC, what we do is that we format the data for modeling. We get the gridded data set from either ECMWF or any other platform that a user prefers. But for us, we take our data from ECMWF, CHAPS data, as I mentioned in the previous slide. Then we format them and prepare meteorological forcing files to run for the two stations that I've selected for this presentation, which is one KA59 and one KA31. Although we are setting up the model as an operational hydrological model that will be able to determine stream flow, power, and strength, and even give historical data for any point or any river reach within the two basins that the user will select once the model is fully operational. Then we interpret the outputs and adjust the results accordingly by calibrating and calculating the biases, and we analyze this output to see how the model will perform. So the data pre-processing steps are all done in a Google Earth Engine environment. So we have already developed scripts within the Google Earth Engine platform that analyze or get the soil data for your specific area that you want. So what you can do in this case, you can define your bounding box, or you can even provide a shapefile for the specific region you want. Then soil data, land cover data, slope, a DM, drainage direction, and mean annual precipitation are all exported to your Google account. Then you can download this and input as a big input. Leaf area index is also exported in the same from the same platform, and albedo. ERA interim data can also be exported from Google Earth Engine, but we have a separate script that does that for us automatically. So I will not really go into much details on the importance of Google Earth Engine because many speakers have already touched on them. So what we do is that we format big input files by creating a snow parameter file. we create a soil parameter file, vegetation library, and also a vegetation parameter file. Then we create a meteorological forcing file that will contain rainfall information, wind speed, maximum and minimum temperature. And the main input file for VIC, after all this, it will be the global parameter file, which in itself will reference where the soil parameter file is, where the snow parameter file is, where the vegetation library is. And in the global parameter file, will define when the model should run, or the period, the start period and the end period of the model run, and will define parameters such as the snow band, and also outputs that we want. We can define if you want, the default outputs are soil moisture, we have precipitation, just to compare how much your model performed. We have a runoff output at a grid cell. We also have base flow and other parameters, since the model can also give full energy outputs. So you can, if you specify the full energy outputs, you'll get other different outputs. So the next step to get streamflow data is that you have to incorporate a routing model. And in getting a routing model, you have to define your flow direction file, which will inform the model how water will flow from one cell to the other. A fraction file, which will tell the model how much a cell, if it's a 5 by 5 kilometer cell, how much within that cell, how much in terms of percentage is that cell contributing to the flow downstream. A unit hydrograph that will define how the cell responds to 1 unit of rainfall. Then the station location file, which is like your PowerPoint in ArcGIS. This determines the point or location that you want your outputs to be given. So in real life, we use gauge stations. If a gauge station exists, we take that as our PowerPoint to help us in calibrating the model. There are other input files that are optional that a user can define. To route, you need the runoff data, which are in flux form, and base flow data. And the routing model will incorporate all these data sets to give you discharge at a specific point. So these are just examples of outputs that we have already achieved in the 2 stations that are selected for the presentation. One example is 1KF59. These are a comparison from observed data and the model simulated data. Before, you could see that the NSE values are negative 193, and for 1KF59 is negative 269. Yeah, but after calibration and comparison to the simulation, you can observe that for a station, for example, 1KF59, there is a significant improvement in the output, and we get NSE values of up to 0.69. And the next station, which I didn't, I forgot to put the NSE, which is around 0.59. So there are other outputs that, as I mentioned, you could also get evapotranspiration, runoff, base flow, soil water moisture in the 3 different layers. You can also get precipitation, wind, net radiation, depending on how you specify it in your output, in your global parameter file. So this is the aim of this or the aim of the work we are doing is to develop an operational hydrological model for the East Africa region, but currently we're working in Tanzania to set up the model. So the next step after having the model running as we want it to run is to have a visualization platform where the basin water officers, the different water basins will be able to access the data easily from their office. They won't really have to go and run the model again. The model will be running in the background on the cloud. What they will only do is access the platform when they want to get historical data in form of time series, flow duration curves, or even return periods of different magnitude items. And if the model is run in a focused mode, which is one of the objectives that we are looking at implementing or achieving, is the model should be able to inform hydrological bulletins, such as give a forecast or a hydrological forecast, or even the forecast in terms of drought within the basin for the next maybe 3 months, depending on the input data that we'll be having. And this information could even help in planning, for example, hydrological power planning or even drought mitigation strategies. Thank you so much, and that's all from me. Thank you.
Thank you so much, Felix Kasiti, for that presentation. I meant to understand that that would be our last presentation today before proceed for lunch. So I don't know whether there is any question for Felix on the work he's doing in Tanzania. If there is no question coming from the group, then we can proceed for our lunch. Otherwise, thank you so much for being with us this morning and this part of afternoon. Thank you.
Lunch is being served down, so you can go down and take your lunch, and then you come back here at 3 for the crossing ceremony, and yes. Now it's too late. It's too late. So you can proceed for lunch, then we come back at 3. And then we will issue you with the certificates after the symposium.